Right? So hello, I am here with Charles, one of our other programming members, and we're going to be just doing a tour of the Lib199 as it stands. So I guess we should just get started. I'm going to try to go through everything here, which is a lot. All right? And oh yeah, chime in if you have any questions because, you know, it'll can then be answered. So I guess I can just go in order of how they're listed here, except actually these first few things won't make sense until later, so we're going to jump here. So this is Lib199 subsystem, which is essentially a class which lets us tap into the robot's periodic and simulation periodic methods from Lib199 where we don't actually have a robot class. So to do this, we just implement subsystem, which actually has these methods. And then what we do is we have this static block, which is going to be run whenever someone actually tries to call something to the class for the first time, which is going to call register on this subsystem, which is going to make sure that it gets added to the command scheduler, even though we aren't part of a robot right here. And then from here, we can just call these register periodic and simulation periodic methods. Should really be called register simulation periodic, but I'm not going to be making changes right now. And they will add a method to this queue, and then whenever there's a periodic or simulation periodic loop, it just calls all of those runnables. One down. Next up, Limelight. Bit longer.
Used,
what?
I never really seen them used though. Are they like?
They are. Good references. So the one that's actually used in regular code, they're used quite a bit in simulation stuff, but right here is like in MotorErrors, which we'll talk about later. We register this periodic method do report SparkMax temp, and I think we also register this check SparkMax errors maybe. Regardless, what it does is it will is this like checks that the SparkMaxes aren't overheating always, and so this way it can be run in periodic. Once again, even though we don't have a robot. All right. So Limelight. Purpose of the class is fairly self-explanatory. We're trying to control a Limelight and get all of the fun methods from it. And so to that end, we have a bunch of stuff here. A lot of this doesn't actually matter. Is mounting angle, find all references. So you're just curious about this. Term and object distance. All right. So one of the main things to note here is that it comes with this class config, which just contains essentially all the different values that you might want to change depending on what Limelight you're using. And so they're all stored here. NT name is referring to the network table's name of the Limelight. By default, this is just Limelight. However, like for this year where we have multiple Limelights on the robot, we might want to change that so that one of them's on one network table, one of them's on another one, so they don't try to overwrite their own values. And so we can change that right here with NT name, and then I'll also talk about how you can do that with constructors. And then here are PID values for steering tolerance, how close is it going to try to align us to the actual target when we're doing auto steering. Steering factor when, I believe this is when it doesn't see the target, how fast is it going to tell it to turn, and that's a percentage. Max steering adjustment, that is the maximum for how much it can tell the robot to turn at a time, and it's just set to 1.0, which is normally going to be 100%, but Limelight doesn't really care about units. backlash steering offset degrees. I believe that is when we go to a target. This will, I think, allow us to, so it adjusts the set point that we're trying to steer to, which can let you change, if we're overshooting the target consistently. Area threshold percentage, how much of the target do we want to be in the vision? So percent of target, which is currently set to above 100%, but in general, area is something we can control from Limelight, and also it doesn't really matter because if you're close to a target, it'll have a large area. If you're farther away, it'll have less of an area, so we don't really need that control that much. And then this is the KP value for distance assist. All right, back up to the top. We have this value idle turn direction, which you can actually set later on in the code. And this lets you change when the robot doesn't see a target and you're doing automatic turning alignment. Is it going to try to turn the robot clockwise or counterclockwise? Then PID controller will get to these things later. So by default, if you just create a Limelight, it will create a Limelight with the network table's name Limelight and a period of 0.02 because that is the robot default, I believe. Yeah. And then you can see that it just sets up all its PID controllers and stuff there. Next, determine mounting angle. Fairly self-explanatory. So it's saying we know that we know that the camera is mounted at some height, the object is mounted at another height, and we know how far away that object is. And by doing that, we can do some math, and based on that math, we can say what angle is the Limelight at. Next up, determine object distance. Lets you determine how far away an object is, and this is essentially on the flat ground distance, so it doesn't calculate how high up it is, but if you have like a robot somewhere over here and a target, say, over here, then what all this code is essentially doing is it's drawing a bunch of right triangles, and it does account for height, but it doesn't return it because we only know we only essentially know, it's hard to do this without 3 dimensions, but what the angle up and down is and what the angle side to side is. And so from that, and then we should be able to know from the game manual how high the object is. And so using all of those values, we can essentially do trig, and we get what the robot will call forward over here and strafe like this. And that is just what's returned. And then you can use that to do driving calculations and all that fun stuff. Distance. What?
You should have. It's like top.
What?
That image you.
What was that? So this is like a top view, yeah.
Top down.
Yeah.
Okay.
And then if it's flat, yeah, it doesn't, because it doesn't do the height bit. Yeah. So distance assist. I don't think we've ever really used this, but it does exist in the code, and what it's meant to do is it's meant to, I believe, drive the robot forward or backward so that we're a certain distance from a target. But again, I haven't looked at the code much, so I'm not going to go into depth there. The one we have used a bunch is this method steering assist, which tries to take the robot and point it to backlash steering offset degrees, but really most of the time that just means point it so that we're looking at the target head on. So in this thing here, I don't know if it lets me rotate nicely. It doesn't. Sad. But basically it would want to get us so that we're looking directly at that target. Yeah. And then to do that, these are just getting the TV TXJ values. You can read the Limelight documentation to learn all about those. put values, just saying put these values on SmartDashboard. And you can see exactly what the value name is going to be there. You can see we account for multiple limelights by saying what the network table's name is, and then it will let you set value TV to TV. This is a simple check for whether TX is NaN, because I don't know if we've ever run in. My guess is we ran into that once, although I don't think that it should be a common occurrence. But basically, if TX isn't an actual number, make it 0. Next, update the PID controller for all of the for all those PID config values. Set adjustment. So TV is whether the limelight actually sees a target. So if it doesn't see a target, because we can go over that one first, it's going to set this flag new PID loop to false, and I'll get over that in a minute. It'll reset the PID controller, and it will set the adjustment to just be the steering factor set to turn the steering factor percentage in the direction of idle turn direction. All right. And then if it does see a target, then use the PID controller to calculate how much we should be turning towards it. And if this is the first time that so if we were just not seeing a target and now we do see a target, then update the PID controller's set point. This line is essentially Java speak for saying don't let adjustment be larger than max steering adjustment. And after all that, save it to SmartDashboard and return the value. Is aligned is the PID controller wherever we want it to be pointing. Auto target, it just combines distance assist and steering assist. Get PID controller, put value. We have a method to get the idle turn direction, and you can also set it with this method here. And then one thing I might want to quickly demo, here I have our robot project. So with regard to using the config thing in Limelight, do we have, where did we store all of our Limelights? Limelight mode. Whatever. Let's switch to a branch where I can do this. Sorry, give me a moment. And it's yelling at me, I think, because of Lib199 stuff. Yeah, there. So with using Limelight and stuff, here we go. This is how you'd edit values in the config class. So you do your limelight.config, and then value, and then it's just a variable. So simple. Next up, linear actuator. So this was a class that we wrote specifically for this year to work with our linear actuators on the shooter, but it should work with any linear actuator. And it just treats it as a PWM source, which is provided by WPILib. So you give it the channel and that it's on, and the min and max length of the PID output. So this just configures that for at least our PWM controllers, or our linear actuators, they expect a pulse width between 2 milliseconds and 1 millisecond. And then based off of that, PWM provides a set call, which lets you set what percentage it's at. And a get call, which lets you get what percentage it's at. And then the rest of this just scales those values by min length and max length, so that we can set our linear actuators to a specific length. Next up, linear interpolation. And this we use a bit. So this year we do it with our ball PSIs, and also anything. And also we did in the past with distances for calculating shooter speeds. And this will linearly interpolate a CSV file. So, yeah. So, where is this? So you can see this year we have all of these CSVs, and what they have is they have a first row which is labels so that we can actually read them, and then they have these PSIs, and they map to RPMs. And so what linear interpolation does is, like, if you put in 4.5, it'll give you a value halfway between 2500 and 2400. So we use CSV parser to do all of this stuff, which essentially says get this directory, which in the robot project is called deploy, and then within there get the file name within it. So that way you can still do directories and such, but that's how it will work. And so when we use it for, like, vendor RPM, SparkPaths.csv directly in the deploy directory, they are stored shooter. You can see we just pass in essentially the file names. Yeah. Then we ignore the first data point, because that is what we've been using as, like, our title value for the columns. Get the X's, the Y's, blah, 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 blah. Calculate, essentially populate these arrays with how many data points there is, and then make sure that they're all sorted by the X value, and then essentially do linear interpolation on all of them. We pre-calculate the slopes and the intercepts, and then when we calculate a value, then we check it has to be within range of the domain data. So, like, for like this value here, if we put in something lower than 2 or above 5, it just won't work. But otherwise, do linear interpolation. If we wanted in the future, we might change this so that it just returns the min or max value in the data set, but that's that. But it doesn't currently. All right. Next up, mocks. So this class was created while we were doing all of our simulation work, and it's still, this is going to be one of the more complex classes in here, but it uses a library called Mockito. And what that lets us do is we can create mock objects. So the main use case for this is, like, if we have something, say a motor, so like SparkMax, then what this will do is it will create at runtime a dummy class, which is, you know, going to be like our better SparkMax, and that extends SparkMax. And then what we can do is then if someone calls a method on the SparkMax class, we can intercept that method and instead feed it to our other class. And this lets you do that at runtime, and also with interfaces that let you essentially map methods even if your implementation class at compile time doesn't extend the SparkMax class. So a bit of a preview for later, like let me keep that open. So like, where's something fun? So like this mock SparkMax class, it has all the set methods, it has the follow methods, but it doesn't extend SparkMax. And what that means is that we don't need to specify a port number, and we don't need to specify motor type and all that when we actually create our mocked SparkMax. And so that way it doesn't do the RevLib thing, which I dislike a lot, which is where if you don't have a motor connected, it will just crash the code. And so it won't invoke any of the super constructors or anything, and it will just map over the methods directly. Of course, that means we also have to be careful not to, well, sorry, never mind that. But yeah, and so you can see that it once again does this register periodic methods, and this is long variable names, But essentially, because Mockito is designed as a debugging API first and foremost, every time there's a method call, it stores a copy of that in a massive list. And so what this does is it clears that list because otherwise the code runs out of memory because it's logging every method call and crashes. And so periodically just clear that list out. And then we have all of these create mock class or functions, which let you create mocks with different parameters. So the basic one that you'll see is this mock some class. So like in our example here, you'll see mock like a SparkMax PID controller, then implementation class. What class is going to actually implement these methods? So we're going to forward all of those calls to this new SparkMax PID controller to our mocked SparkMax PID controller, which has all of the methods in it, and I'll explain how it checks methods in a bit. And then here we have an answer value, but in the one here we have interfaces, and the answer value is here. Lost my train of thought. Yeah, so interfaces, basically in Java, a class can extend stuff and it can implement stuff. So this lets you pass things into the implements section of that method. So it's going to map all the methods of this class onto a class which extends this and implements all of these. And in case you're unaware of the ... specifier, that just means that we can have a bunch of classes. So like, you can have like a create mock. I was doing CanSparkMax .class, and you have to include the .class because we're looking for a class object and not a instance. And then new implementation class. And then, like, what are some things it can extend? So it can extend, I'm now running out of names. I can't remember interface names. So, like, I don't know. Not that you'd ever want to do this, but, like, serializable.class. That's an interface. And then also, what's another one? I don't know. Another interface.class. And you can just do this as many times as you want. And there you go. And then it returns it to here as an array. Like that. And then what this does is it will call it onto this method, which does the exact same thing, except it gives you access to this boolean, which is forward unknown calls, which says if there's a method which isn't included in this class or in this implementation, that's still a part of either of these classes, because I'm pretty sure it does the interfaces as well. I don't know. It might. Well, hang on. Yeah, no. So it does both the classes and the interfaces. Sorry, it can mock methods on both the classes and it can mock methods on the interfaces. So if there's a method which is defined in either this class or one of these interfaces that isn't implemented in this class, then what do we do with it? If it is true, then it will go and just call the originally defined method, which can be dangerous because, remember, we skipped calling any constructors, so stuff might not be initialized and stuff might break, but you can do it. And if it's false, it will just do this thing, which is return smart nulls, which basically means it is going to return a null value that's like specific to the type. So if it's an integer, it'll return 0. If it's an object, it'll return null. If it's a boolean, it'll return false. All of that stuff. And it won't run any code. And then all of that goes to the main method here, which does the same thing, except you get this default answer, which is the same kind of thing you did here. And return smart nulls is one of these things. It's a default answer. So what that means is that it's just a generalized way of saying how are we going to call a method if we don't know, if it's not defined, right? So what does this do? So how does this work? We have this thing which is list methods which is going to say get the names of all of the different methods on this class that we're extending and this class that we're implementing. Next, because we're creating a new class that's going to extend this and we're going to return an object of that, we can't mock static methods and we can't mock final methods because we can't extend those. So if there's a method which is either static or final on either of these things, then don't even try. Otherwise, then see if there's a method in our implementation class which has the same name and the same parameters and also the same return type. Or really what isAssignable from means is it means a type or a subclass. So like if I have if there's a method which is returning a speed controller, then this will accept something that returns a speed controller or something that returns a SparkMax or something that returns a Talon, etc., etc. And yeah. 1 second, I think I think I had my volume way too high in the recorder. Sorry if my audio before was bad in the recording. Continuing. If you've defined a method which has the same name and the same parameters but doesn't have the same return type, it's going to yell at you because that's probably a typo of some sort. And then we are going to add into our list of methods essentially something that says, here is the method that we are overriding in the original class. And instead of calling that method, we're going to call, I just defined this type, invocable method, which is basically, what are we going to call this method on instead? All right. I hope that made sense so far. And then mock settings is just how we add interfaces. So if there are any interfaces to add, then add them to the settings. Otherwise don't. And then we're going to set the default answer, which is how we're going to be implementing all of these methods as a mock answer, which I'll get to in a second. It's defined down here, which takes all of the methods that we've overridden, the class, and really this is an object that is going to be, that we're going to be passing all of these method calls to, and the default answer that I talked about before. So if there's not a method, then what are we going to do? And then we are going to go down here and call mock, and there are a bunch of different forms of doing that, but basically they make sure that they all go through, let's see, what does this report mock do? Mockito mocking details, it's mock, hang on. Oh yeah. It's going to mock that class that we wanted to extend with all of the settings which specify how we're going to override all the methods, what it's going to implement all of that. And what it does is it makes sure that we just pass that call to the underlying mockito.mock method, which creates the mock, and we pass it to report mock, which stores the created mock object in an array of mocks, which allows us to do that clearing of the calls array that I talked about earlier. We also make sure to use weak references here, and that's because if there's a mock and it has no more references to it, so like we have class something, I don't know, there's a number of ways that you can get that. Basically in Java, Java handles garbage collection for you. So if there's a way that object is no longer used by any part of the code and Java decides to delete it, it will get removed from our array, and we don't have a reference to it that's just taking up memory and not doing anything. So yeah. And then the last part of this class is this mock answer method. You can see it takes in all of the methods that we will want to use, the implementation class that instance that we're forwarding it to, and a default answer. And then the bread and butter of all of these default answer classes, because remember that is what this is under the hood, it's an answer that's going to say, how are we going to answer any invocations? If for every time we have an invocation of a method on our new mock, if the list of methods that we took from our implementation class and that we are mapping over contains that method, so if we overrode that method, then get the new version that we instead want to call on our mock and invoke it on the implementation object. So over here on our mocked object, which contains all the methods, and call it with the arguments that were passed to the method. If an exception occurs, then just throw it back to the caller because not our problem. And then if there's a method that we didn't, and return the result. And if there's a method that we didn't mock, then instead use the default answer and ask it how should we answer this invocation. All right? Did all of that make sense?
So this is a very complicated way of just making your own class version.
What? What was that? Making
this is a way you guys make it really complicated to just make your own version of a certain class.
Yeah, exactly. And so you can see that, what we then do is then we create classes which have our implementation classes look something like this. They can have their own local variables which are defined in the constructor, and then they have public methods which return stuff, which have the same name, which have the same arguments. And then mocks just make sure that we call these methods instead of the actual things so that we can avoid constructor calls and all that, because that otherwise we're allocating objects in some libraries, particularly Rev Robotics, do not like that when we don't have an actual motor connected to them. All right.
So if you could add additional methods.
What?
You can also add additional methods.
No, you can't.
Bro.
Well, no. The reasoning behind that is that it doesn't return the implementation type, but in our MockSparkMax example, it doesn't return a MockSparkMax. It returns an actual object which is a CanSparkMax, and the CanSparkMax definition doesn't have more methods added to it. It was defined at compile time, but at runtime we can remap what those methods do.
All
right.
I never knew you could do that.
Yeah.
That's just
this was the effects of our simulation research. All right. Now back into the realm of code that you'll actually see used much more on the robot, although you'll see that class pop up a few times. MotorControllerFactory, you should hopefully be familiar with this. It has all these methods in it which will take a motor type, so Victors, Talons, and Sparks. And they first of all do this little check here, and here's where mocks are going to come in. If we're running on a real robot, then just create it as expected. Otherwise, we're going to create one of our mocked versions, and this else case happens in simulation. So then in simulation, we'll create a mock which will, properly respond to any method calls that we want to work in simulation, and also make sure everything's being passed over the WebSockets API so that it can, be edited by our external simulators that we used.
One question. Mm-hmm. So you guys use Mockito for debugging or whatever?
It's supposed to be used for debugging, and we use it to essentially hack into method calls and make it so that we can run our own code without having to take every bit of our code where we say, here's a CanSparkMax, and replace it with, here's our better SparkMax implementation.
Okay. So it's like completely non-affiliated with WPILib.
Yeah. It's completely different, just a library we found on the internet. Yeah. And so what this will do is this, and so then you'll see that these methods set all of the configuration values on the motor that just make sure that every motor's in a default state. It enables current limits, sets PID values and such, and it passes it all to this MotorErrors.report error value, which I'll get to in a bit, but it essentially just says, was the error code a nothing happened error code, i.e. it worked? If it worked, then just let it go on. Otherwise, go and yell at the user that, hey, code's not working. Yeah, and then the other thing to take note of is that when we're creating a CanSparkMax, we also expect a temperature limit on it. This comes from our long history of breaking SparkMaxes. And so just from testing, we've created 2 which work fairly well for their respective motor types. There's one for Neos, which is 70 degrees Celsius, and one for Neo 550s, which are smaller, and so it's only 40 degrees Celsius. And so you can pass in one of those here, and it will just get out whatever value we assign to that motor. And so we can change those values in temperature limit without having to affect the rest of our code. And in CanSparkMax, we have, and then we can also pass in just a number if we want to use a number instead of one of the predefined values, and that's in Celsius. And another note here, most libraries, like the vastly, all right, I'm going to stop bashing Rev, or should I? Like the Phoenix library, when you pass in a motor that isn't connected to the robot, it will say, there doesn't appear to be a motor here. Hey user, I think your code's wrong. But some libraries, mainly Rev's library, if you have a motor which is not connected to the robot, and you say, and you try to do something with it, it will go crazy and kill the robot code with some crash in their C++ API. And so to fix this, if the firmware version on the SparkMax is 0, then that means that there's not a SparkMax actually there. So then just close the SparkMax, which means don't say there's no SparkMax here. Ignore that Spark that we created. Yell at the user because there's not a SparkMax there, and then create a DummySparkMax, which I'll go over in a bit. And then if we're in a simulation, do our simulation stuff. And down here, we also do report SparkMax temp. So this just tells MotorErrors, hey, we created a SparkMax. The user requested that this be the temperature limit. Do whatever you have to do. And then also here, check SparkMax errors. This does another periodic method which will ping the faults and sticky faults of the SparkMax. Read RevLib to figure out exactly what those are, but they're basically just different errors that can occur with them. And if something happens, then notify the user something happened. Again, we'll talk about that later. And then the final ones here, we have one that creates a cancoder. And once again, there's a simulation equivalent for that. And the mocked one is actually slightly different than the other mock classes because Phoenix has stuff which generally plays nicely with simulation. So what we can do here, well, I'll get to it later, but basically we don't need to actually override any of the methods that they have. We just have to make sure that the data gets pushed out to the simulation. And then we also have a USB, some cameras for getting USB cameras off it. Yeah, basically configure camera is going to create a camera. If you've already asked WPILib to set up a USB camera, then it won't do it, or then it will just do the next one on its list of USB cameras. So if you have like N cameras connected, you can just call configure cameras with however many USB cameras you have, and it will get them all, put them in an array, and give them nicely to you that way. And what this also does with like this camera server stuff is it lets you access those from SmartDashboard or from whatever its driver station window thing is. And you can do all of that just, you know, where do we use that in our code? It should be up here. Where is it? Yeah, so you can see right here we have one USB camera on our current robot, and we just call configure camera once, and then it sets it up. Done. Whoops. Calculators. Yeah, and then, I completely forgot to go back up to the top here, so I'm going to do that before I forget. This will now make some sense now that I've explained Mockito. Actually, this one doesn't require it, but basically, if you noticed in MotorControllerFactory, when we create a SparkMax, we actually create a cached SparkMax. And what this does is it just extends CanSparkMax, and it overrides these getEncoder and getPIDController functions, and just caches the value of them. So when you call it the first time, it will call it on the actual method, and after that, it will just return whatever we had before. And the reason behind that is because RevLib was, again, I don't know why they did it this way, but every time that you call the getEncoder method or getPIDController method on a CanSparkMax, it will go through the work of allocating a new object and doing a bunch of can work to make sure that it's synchronized with the motor, which eats up the CAN bus and also takes up, you know, a lot of processing time, especially when we're doing this in a periodic loop on most of our subsystems. And so this means that we can just call those getEncoder and getPIDController methods. I think we still cache them over here out of habit. So like in Drivetrain, oh wait, no, because it would be in SwerveModule there. Like an intake feeder, we still, let's see, we still just store them in variables. But now, especially when people start writing code for the first time, they will just write spark.getEncoder in a periodic loop. And this way, that doesn't completely break everything, I mean, or take up a lot of resources. Yeah. And then the other ones I wanted to go over, DummySparkMaxAnswer. This is when we have that DummySparkMax thing that we created here, where we're on a real robot and we just tried to create a SparkMax which doesn't exist. Then what this will do is it says check what return type we were supposed to get, and this just implements some basic types. So if we were supposed to return an encoder, then return our cached mock of a relative encoder, which returns a RevLibErrorAnswer, and I'll talk about that class. I'll do that next. If it's supposed to be an analog sensor, then do an analog sensor limit switch, return a limit switch, blah, 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 blah. Otherwise, return a just a general RevLibErrorAnswer. And that's what all these do. So in not so many words, it checks the return type of a method, and this says if it's a rev-specific object, then return a mock of that object with a RevLibErrorAnswer. Otherwise, just return a RevLibErrorAnswer. RevLibErrorAnswer just means it returns there was no error to anything which was an error or which requires that answer. Otherwise, just return the smart nulls thing, which means don't do anything, just return its equivalent 0 value. And that means that we can like call on our dummy thing, like get a PID controller and then call methods on that PID controller without getting a null pointer exception. And then there's some other stuff for like defaults of it's going to be a brushless break, so blah, 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 blah. Doesn't matter.
Can we just not use RevRobot?
What?
Can we just not use RevRobotics, man?
I have many times asked myself the same thing. Alas, I think that Senac very much likes their motors. Also, they have some nice features if you ignore all the bad API implementation. But, yeah.
Also, in the MotorControllerFactory? Is it so like there's CachedSparkMax?
Mhm.
I don't remember you have to.
What?
I don't remember that you had to put a temperature limit for the construct.
Yeah, it's usually glossed over because you can write it in fairly quickly, but in the past we didn't have to. And then let's see when I introduced this change, April 4th. So since April 4th, and since whenever this issue got merged into master, you've had to add temperature limits.
And also for the talons.
Yeah.
There's no temperature?
Well, the reasoning for that is that the motors here have, or like the Neos and stuff, have temperature sensors in them, so we can detect if they're about to burn, whereas the Talons do not. And so on that one, we just trust Senac and program to work together and not run a motor at a speed that's going to break everything. And so, yeah, because we just can't check the temperature on these. And, you know, that's also kind of, and then we also try to control that with current limits, which we also have down here. And also just, nowadays we are basically using exclusively SparkMax, at least for the moment. And so, you know, everything has a temperature limit. But yeah, we just can't check it. So back up to here, ErrorCodeAnswer. I showed you RevLibErrorAnswer. This is the same thing, but for the Phoenix API. So it's the same thing for an error code. In fact, hang on. We can actually look at these side by side, and you will see that they are very much the same. Yeah. Okay. There we go. That takes us through. We've gone all the way down here. So motor errors. All right. Yeah. So this is a bunch of stuff arrays at the top. We can talk about that later. Essentially, make sure that we are doing the report SparkMax temp method every periodic cycle. Here's the report error stuff you saw from MotorControllerFactory. Basically, if there's an error which happened, if there's something that returns an error, call it to this report error method. If the error is null or the error is OK, which for Phoenix is this and for RevLib is this, then do nothing. Otherwise, tell the user error code while configuring either CTRE or Rev Robotics motor, and then here's a stack trace because why not? All right. Next up, check SparkMax errors. So this is run, I believe, every periodic cycle. Print SparkMax error messages. Oh wait, this is not directly run by, I think, this is actually done in, yeah. So in our robot periodic classes, we have this here. I guess if we wanted to, we could port it over to Lib199 subsystem, but just when we created it, that didn't exist. So in our robot periodic method, we call print SparkMax error messages, which for each SparkMax goes and calls check SparkMax errors. So what does that do? It gets the faults and the sticky faults of the SparkMaxes, which are all the different errors that occur. Sticky faults just means it persists over, I think it's restarts, or maybe it's just throughout the life of the program. Again, check RevLib docs. If flags contains keys, so then get the previous values, and what that means is that like if there's a like no encoder connected fault, I don't even know if that's a real one, then that means that for the life of the program we don't get a bunch of there's no encoder connected, etc., 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 and we just say it existed once, it's gonna exist in the future, ignore it. And then is not zero just means there is a fault, and then print out. This is Kevin's amazing error message. Basically, there was a fault on this ID, and then it does some formatting, which essentially converts these numbers into the actual names of the faults. All right. then try and clear all the faults on the SparkMax if we can, and then update the faults values. So if there was a new fault, we now flag it so that if it happens again, we'll just ignore the message. And if a fault disappeared, then when it reappears, it won't be included in the previous values, and so it will have an error message, right? And then...
Okay, so like you're just not doing repeated errors?
Yeah, unless it goes away and comes back.
Wait, how do you tell it goes away again?
Every single time, you can imagine all the different faults are stored as a number, which changes with what types of faults there can be. This is, I'm pretty sure it's just the bit stuff I was talking about the other day. But basically, if the number is the same between 2 runs of this method, then that means nothing changed. If it did change, then that means a fault either went away or came back, and so if it's not no faults, then we'll yell at people again. But otherwise, if all the flags went away, then these numbers will go back to 0. And so then when we check it next time where there is a fault, 0 is not equal to whatever our number with faults is. All right? Make sense? All right. So then here's our DummySparkMax thing. Basically, you can see that in our DummySparkMax answer, we just defined a mock, and you'll see this a lot with these names where essentially we define it once so that we don't have a bunch of mocks which all are the same value but which all do nothing, or which all are the essentially same value but are different objects which all do nothing. And so just create it once and then ignore it for the rest of the time. So then you can see this is how we actually, when we get a report SparkMax temp call, it says check the temperature on this spark with this temperature limit. So store the following data, which is map the ID of the spark to the spark. So if so we can get the spark by its ID, and you'll see why we need the ID later. It's just for error messages, I think. Yeah. And then also map the ID to the temperature limit for that spark. And the ID is just the port. All right. And then do report SparkMax temp. This is the method which is called periodically. So
my computer just shut down because it was at 7%, so I was gone for like a minute.
For like what?
Did I not leave the Discord call?
You didn't.
What? My computer literally shut down.
My guess is Discord was like, oh, he just lost connection. I'll wait for him to come back. So how much did you miss?
So you were just talking about, you just finished talking about like how it checks whether the error is.
All right. You didn't miss much. Basically, I was talking about how in DummySparkMaxes and such, you'll see that it caches this DummySparkMax that does nothing and all of these other objects which do nothing, because if we create a new one each time we needed one, then in memory we'd have a bunch of objects that all do nothing, but which are all individual objects. So just create it once and then forget about it. And leave it so that if we ever need it, we just pull it, and yeah. So here, yeah. And then I was talking a bit about how report SparkMax temp, what we do is we get the spark, the temperature limit, and we map the port to the actual SparkMax object and the port to whatever the temperature limit is. So then in our periodic method, which is do report SparkMax temp, for each SparkMax, get the port that it's on and the SparkMax object. Here's the temperature. Use that to update the SmartDashboard value for it. And then if the temperature is above what the temperature limit is, or it's a SparkMax which has previously overheated, and this means that if we have a motor where like it was stalled and it overheated to the point where it tripped the temperature limit, it doesn't then cool down to below the temperature limit and then get turned back on and then go back and hit the temperature limit, possibly breaking the motor eventually. So if it's overheated, it is going to stay overheated until you restart the robot code. So if it has just overheated for the first time, then flag it as overheated so that we will never use it again. and and then print out to the console, hey, it is operating, that SparkMax is operating at very hot temperature. We are going to shut it off. And then we are going to set the current limit to 1, which means it will be able to draw no more than 1 amp, which basically means, for all intents and purposes, it is stopped. And what this also means by repeatedly resetting it is it does 2 things. 1, if another bit of code calls a set call, it's not going to be fighting for control of the motor by being like, set it to 1, no, set it to 0, blah, 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 which could maybe still have it running. It'll just say, you know, have the current limit here. And if another bit of code tries to update the current limit, then because this is in periodic, it will update it. And then before the motor can even really get going, because we shouldn't be setting a current limit in periodic, I hope, then it will get the current limit back down to 1 so that it stays stopped. All right. Then that is motor errors. All right. One more down.
So for motor errors, you guys have like a kind of like a main function that's in periodic.
Yeah, basically. And yeah, so this function you can see is going to be called, it's just defined, are you aware of static blocks?
Those just run when it's initialized, right?
Yeah. So when it's initialized, register that as a periodic method. And then at some point what we should also do is probably set that up for print SparkMax error messages. But for the moment, it's just convention to put print SparkMax error messages in robot periodic. So, oops. So right here.
I mean, you could just like add it to periodic like you did with the other one.
Yeah, exactly. We could.
Okay.
I'm just not making API changes right now, but you'll see there have been a few times in here where I've mentioned we could probably change it to this and it would maybe be a little better. But at least I haven't seen any glaring issues. So OmniDrive, this was made, I believe, for dry run last year or something like that, wherein we more or less wrote it as an exercise and it's never been used, but we saved it because it is a drive. And so OmniDrive, essentially, you can look up exactly what it is. If I recall correctly, it's kind of like Swerve in that you can move in any direction. Let me get a new paint window. But basically you have like you have your robot, and if I recall what OmniDrive is correctly, you have a wheel here, like that, a wheel like that, a wheel like that, and a wheel like that, and they're actually fixed at these orientations, and they're also Omni wheels, and so it's basically Swerve, but not as good as Swerve. And then this is based off of this WPILib class, which we basically just copied and edited so that this is the one. If you saw, this is this. That one I believe is for when you have one with it's for when you have one with, I think it's like supposed to be like this, where you have 3 motors. And so we just edited the code so that there's 4. And now we have OmniDrive. And yeah, and this is based off of the, like, if you've seen the differential drive class pop up in some of our old code, it just lets you drive. It just provides these drive methods, which, you know, do it. Yeah. All right, we went over RevLibErrorAnswer, SparkVelocityPIDController. That's a name. So this is basically set up to do velocity control on a PID controller. And this was made primarily to work with our shooter this year. So you can see that in like shooter, where is it? Here it is. We just create one of these and it will handle all of the work with mainly it's a bunch of SmartDashboard work, but it does some other stuff. So you can see it takes in a name for this controller, or really a name for what this thing is doing. So in here you can see it's shooter, the SparkMax that we're going to be running on, as well as a default p-value, an i-value, a d-value, a ks, and a kv. Ks and kv are more motor constants, kind of like PID, but not really. They're specific to the motor. Or no, they're not. They're like PID, but they're more values. And you can, I don't know, WPILib, KS, KI, KD, or no, KS, KD. Yeah. So you can go and read all about what this is, but, you know, it's, I just closed that. I meant to keep that open, minimize. All right. So yeah, then set all this up, set up the PID controller, put everything to SmartDashboard, and then this set reference value is what actually controls what PID we're trying to get to, so, or what value we're trying to get to. So you get the target speed, we're going to be controlling this as velocity, so RPM. 0 I'm sets to, what is that? It's a PID slot. So that's if you have multiple PID controllers, but for all of our SparkMaxes, it's just the one. So that can always be 0. And calculate feed forward, which does that calculation with KS and KV, so you can see how it's used. Basically, KS is kind of like your default value of always apply this much voltage to the motor in whatever direction of velocity you want to go. And KV is proportional to velocity. And this will just be added on to whatever the other values of, to whatever the other PID calculation is. And that's why it's a feed forward. So yeah, basically that means this is the actual target. This is what our guess is for the speed. Because most motors follow that idea of some default voltage and then some more voltage proportional to velocity, and then essentially do PID on top of that. So if our guess isn't close enough, then PID tune it to exactly where we want to be. All right. Next.
So this is feed forward.
What?
Feed forward.
Yeah, this is feed forward.
Oh.
So then PID, this is the SmartDashboard code that we kind of wanted to get away because, you know, every time we wanted a velocity PID, because you can see that it not only comes up in shear, I think we also used it in intake feeder. Yeah. So, you know, once again, it lets us make all this simpler. So yeah, PI and D, do that. And then here's KP, KI, and KD. Sorry, my brain just shut off and started talking without thinking. So basically, get the values from SmartDashboard, put the values, and take the SmartDashboard values and update those into the PI and D values on the controller if they change. The reason we're only doing this if it changes is because I believe it will send a CAN signal every time you change the values, and so this way we're only doing it if it needs it. So keep note of what those are so that we can check if they changed and do the set P, set I, and set D with whatever we grab from SmartDashboard. Next up, use SmartDashboard to let you get the target speed and call set target speed with that, which actually puts it back to SmartDashboard, so more of SmartDashboard stuff. But update the target speed from SmartDashboard if it changed. Update the tolerance from SmartDashboard if it changed, and then put the current speed to SmartDashboard. Then you can see we have a check for is it at target speed, and this is useful for when when a ball goes through and passes by any of our motors. This can be either in the feeder or in the shooter. It will actually create a noticeable drop in the target speed, which means that we can check, hey, target speed went down, there must be a ball that went through. And so this is how we do like shot logging, and also there's another implementation of the intake feeder default method, which no longer works because we've made so many other changes, but which checked whether a ball had gone through based on when it detected that speed going down. Then there's also a set target speed, which we can call from the code when we want to change the target speed. Think like on our current robot, this is like long shot. So when we want to change the target speed of something, if it didn't change, then what in the world, do nothing, because we don't need to change anything. Otherwise, update it on SmartDashboard. Update the target, update what we're saving the target speed as, and recalculate the feed forward and update the target speed in the PID controller. And then similar idea kind of for set tolerance, but this isn't called as much, so this doesn't require a call to the PID controller, and so you just update tolerance whenever it changes, or whenever anyone requests that it change, even if it's the same value. And then there you go. That is the PID controller stuff. All right. If you give me one moment, I'm going to go grab some water. I'll be right back. All right, sorry, I'm back. Now, fresh with water. Now, where were we? We had just finished SparkVelocityPIDController. All right, SwerveConfig and SwerveModule should probably go in the Swerve package. Again, we haven't changed it yet, so maybe something we can do between this year and the start of next season. But basically, what we noticed was in our SwerveModule class, which is here, this thing just took in a bunch of different values that were basically the same on all the different motors, and so and which were also the same with every robot. So essentially, it took in a massive number of things, which were basically a robot profile, and so we just packaged all of those into one class that you can read here if you really want. But one thing I should probably note, kvolts, kvels, kxls, that's another name for ks, kv, and there's another one, ka. And so again, it's basically PID values. And then here are, here's PID values for the drive motor, PID values for the turn motor. It takes in gearing, wheel diameter, all this stuff, inversion values. Again, it's supposed to be set once and then it's just set up for the entire robot. So if you look in our current code in constants, we just have this here at the end, which is SwerveConfig, which is just taking in all the stuff we defined above and passes, and yeah, it's just set up here, and then whenever we need it in Drivetrain, it just gets past constants.SwerveConfig. And yeah. Oh, and one more note, you'll see that a lot of these are array values, and what that means is that like for K forward volts, it does the one for the left, the one for it has one for each wheel basically, and the order of those is we can see in constants is right here. We should probably have this documented somewhere else, but basically front left, front right, back left, back right, in that order for all the arrays. And yeah, you can see they're all there. Yeah, all right. And now SwerveModule. This one's also a pretty crazy class, but you know, let's look through it. So basically, it will take in that configuration thing we talked about earlier, a module type, which really means which module is it. And here you can also see we have that same order of the arrays. And so everywhere you see an array value for this stuff, it's always going to be front left, front right, back left, back right. That includes drivetrain, and it's just the order. It takes in the drive and the turn motors, the cancoder, which is the cancoder, which is the encoder. I didn't write this class, so I don't know what all of these things are, but that is why we have code. So drive modifier is, yeah, that was very helpful. Let's see here. Where's this used? It's used once down here to set it here, which is then used here. So basically it is, drive modifier is basically a scale on the max speed or on the speed value, which, yeah, I guess it's just one. We probably changed it at some point in time, and that's why it exists. Then also takes in a max speed, array index, which we could honestly probably get from the module type, and we probably should, but basically it's that same idea of that just stores which position is it in all of these arrays. So while we have this default thing, Yeah. Well, we have this default ordering. Basically, you can change it. So, like, if you want front left to instead be in the third position, sorry.
Did you see my? Oh.
Oh, what?
iMessage. I was gonna be gone.
So. You did?
Yeah.
Say something because I'm recording. I have my Discord in streamer mode, which means that I'm not getting any notifications.
Oh. Okay.
Yeah. How much did you miss?
So, like, you just finished talking about SparkVelocityPID controllers?
Okay. Sure.
Well, like, you're recording, right?
Yeah, I am. So, I'll give you the 5-second version. Basically, SwerveConfig contains everything which is based on the robot. So this is basically all the values from constants. And so if you go to our constants.java file, at the end we just have a SwerveConfig, which basically passes in all of the values that we defined up here and puts them in a single object so that our constructors aren't massively long, except for this one. All right, that's the 5-second version. And then I was also talking about how these arrays are ordered front left, front right, back left, back right. However, you can, if you want to change that, even though that's how we've done things, you just change what you pass into array index. So basically, if you instead want like the front left motor to be in position 2, then instead pass in a 2 here, and it will read everything in that way. I don't know, but yeah, there you go. All right, then next up there's this pitch degree supplier, which I believe just means a get heading function, but I will double check that. Again, I didn't write this code, so init pitch, init roll. All right, oh yeah, I remember. So these pitch and roll stuff, along with, you'll see if you look at our constants file, like this mu stuff and some of that, are because during COVID, we were running this not on our nice level field, but out in the middle of a street, which has like slope and all this weirdness. And so those values are run into the calculations to make sure to essentially make it so that the robot will move as if we're driving flat, even if we're not driving flat. And so in our current code, those are just always 0. All right. And then next up, yeah, so code. I actually don't know why we have a timer here. What's this doing? Setting angle. Oh, I know why we have a timer here. We will get to that. So basically, convert the type into a module string. Really, we could probably just do module string equals type.name, but what in the world? And this is basically used for like SmartDashboard values so that we know which module we're talking about. Ideally, in the future, I might want this to implement sendable, and then we can just have it all nice and organized, but whatever. Then, position constants. Yeah, I actually don't know what all this code does because I didn't write it, but let's figure this out. So basically, this is doing the position conversion factors and using it so that we get the encoder in the correct units. So it takes into account the gearing and the wheel diameter so that we get everything in. It's probably meaning to be, yeah, meters per second and meters. Copy the inversion values. This is more physics stuff that I'm pretty sure is meant to, yeah, I actually don't know what all of this is. Oh wait, this is calculating a current limit. Yeah, and then we use that, and then we pass that into our current limit, but if it's a current limit that's more than 50, then ignore it. I'm not going to go and try and figure out what all this does. Basically, it does current limit. Then these are, if you saw our feed forward thing before in here, you saw our feed forward thing here. This is the WPILib class for it. So it takes in the KS, the KV, and the KA, and we create one of those for going forward and for going backward because, like PID, it just makes everything drive nicer. do a PID controller. I have no idea why they multiplied this by 2, but you know, what in the world? It works. Turn controller, PID controller. So this is for when we're trying to, for turning, then, you know, essentially configure a bunch of max velocity stuff and use trapezoid profile and profile PID control. Profile PID controller actually uses a trapezoid profile under the hood. If you want to figure out what all that is, it's more like similar to PID math. Read the WPILib docs on it. It's weird. Enable continuous input. Basically, according to the turn PID controller, it's going to tell the turn PID controller you're going to be receiving values between 180 and negative 180, and it's just a circle. So 180 and negative 179 aren't a million degrees apart. They're just, you know, they're right next to each other, basically. Set the tolerance. Again, this is configuring the turn encoder. So again, minus 180 to plus 180, minus 180 to plus 180. Yeah, and then more setup stuff. And they also have a periodic method on the swerve modules. Actually, I don't think I talked about how the periodic method on SparkVelocityPIDController is used. But basically in like intake feeder, when we have SparkVelocityPIDController, you just call the periodic method in here as if it was because it basically does all the SmartDashboard stuff. And so that happens in periodic, so call the periodic method. Same for drivetrain. For each module, call the periodic method. All right. Swerve module. Trapezoid profiles. So yeah, basically do all of the PID and trapezoid profile calculations that I don't fully understand. This is updating. Make sure that we're driving in a way that is going to be nice and not going to like jerk around and try to drive much faster than we can and such. So apply all the max values, apply all the PID stuff, do all of that, and then but turn volts. What's this from? Simple motor feedforward. Oh yeah, and then this is basically saying if we have to turn, do it using the PID controller. Otherwise, use this simple. Otherwise, just return whatever was from the simple motor feedforward. Wait. Previous turn velocities, turn correction velocity means previous. Yeah, you can work out what all this does. Basically, though, it's a funny way of saying do all those calculations and figure out what velocity we should turn at, and then convert that to a voltage using the simple motor feedforward and make the motor drive that. More stuff to do that. Again, work out all the math on your own time. Then log the positional error to SmartDashboard for debugging. And now here's the main method that you'll actually see used, which is move, takes in a speed and an angle, update the speed, and then if that speed is 0, i.e. don't move, then don't bother turning the module to some angle because it doesn't matter. Otherwise, take that angle, clamp it between 0 and 180, set the angle on it. Anti-gravitational stuff, that is more of the code from when the robot was not running on our nice flat carpets. Then set speed is going to actually set the speed of the drive motor. So, you know, multiply by the drive modifier I talked about earlier. Compare that with the current speed, and once again use the forward and backward, use the feed forward calculations. And also, if you think about a turn module, if you imagine a turn module that's driving forward at 0 degrees, your module is going to read 0 degrees and it's going to drive forward. However, if you then want to drive backward or drive forward at 180 degrees, then you can instead drive backward at 0 degrees. And so there's also some, and so that's, I believe, what some of this code is doing. Yeah, I know it's in here somewhere, but it's going to essentially do that calculation so that we aren't doing unnecessary turning of the wheels. Yeah. Again, apply PID stuff to it. Set angle. This delta t stuff is, I'm pretty sure, being used to calculate like the velocity. Again, make sure that we're capping to within what we've defined our robot's max speeds and accelerations to be. Turn the minimum amount of angle in order to run. I.e., if you imagine your module's at like 45 degrees and you tell it to turn to 180 degrees, instead turn it to 0 degrees because, it's the same thing. Then update what we say all our angle, where we want our angle to be, and there you go. Get module angle is going to be returning the absolute position of the turn encoder minus this turn 0 value. Yeah.
So wait, so this entire class is just for like one module, so like
yeah,
one
and then
of the swerves.
Yeah, and then if you look at like drivetrain, we make 4 of them.
Gotcha. All right.
Yeah. So then get module angle. This uses our cancoder to get the absolute position. This is one of the reasons we use cancoders, is that they are absolute encoders. So we know when the robot is powered on, where the wheel's pointing. And an important note here is that, two notes I wanted to make, and neither of them are really that important, so I don't know why I said that. Subtracting turn 0, this is because I'm going to get to my notes in a second, is because the encoders, when the modules are pointed forward, the encoder doesn't necessarily read 0, so this just accounts for that offset. One thing that I noticed while looking through the Phoenix stuff is that there's actually a setting on the encoder, like how we can set the CAN IDs through Phoenix Tuner. There's also a setting on there that essentially sets this value, so we can maybe move to that if we want, but for now turn 0 works. And to actually calculate that, it's a pretty advanced process. We take the robot, we put it up on some blocks, we get a piece of wood, and we stick it, and we push the wheels against it so that the wheels are aligned to forward. We read what the value is that's recorded, and we write that down. Very complex process, takes definitely one of the more complex things we do on the team, and then we write those down into here. And another note is that then when we drive it, before we drive it, we then push all the modules forward, and if one of the modules is driving backward, then we just take this angle and we flip it by 180 degrees. And so, yeah. And that way they'll all be driving forward when they're told to drive forward. Okay? And keep in mind, all these should be between negative 180 and 180. I feel like I was going to say something else, but I absolutely do not remember what it was. Let me think for it. Oh, yeah. And then another feature that we want to add to this in the future is, at least currently, our cancoders are of the sort where when they're getting jostled around, they'll occasionally get disconnected. Not at all often, but sometimes. And during a match, we don't want that to happen. So we want to maybe add something to SwerveModule which says cache the absolute position and then map that to the relative encoder on the SparkMax. And then essentially, if the turn encoder, if the cancoder goes offline, then instead use the value reported by the SparkMax. And for determining how it's offline, there's not a specific method to do it, but I was thinking we could just use if the angle is exactly 0, because if it's exactly 0, either because we should be constantly making sure that the two encoders are at least in sync. If the angle is exactly 0, any value reported by the SparkMax encoder shouldn't be that far off. And as soon as it moves, it's going to switch back over to using this encoder. All right. There we go.
Right, so what was the turn 0 thing again? So I didn't really catch that.
Yeah, so the cancoders, when the modules are pointing forward, that isn't necessarily the absolute 0 point of the cancoder. So turn 0 is just what the cancoder reads when the modules are at 0. And so it accounts for that.
Okay.
And then I mentioned that I'm pretty sure there's an equivalent in the Phoenix, in like Phoenix Tuner where you can set that. But for now, it's just in the code. So, next, this just converts the speed and angle into a SwerveModule state, which is a WPILib class. Yeah, the speed, update SmartDashboard, puts all of this debugging stuff to SmartDashboard. And if you look in, where's Drivetrain? Let me see if it's there. No. All right, let me go up to the periodic method. Give me a moment. Am I going crazy? Or not implementations? Yeah, there it is. So basically, because it's a bunch of stuff to SmartDashboard and it's pinging motors and such, it will take a bit of time. So if you've seen the loop overrun errors that appear in our robot code when it's running, it just makes them worse. But if you want the debug info, it's not a huge problem. So yeah, you can see that if you want it, you just uncomment it in here and it'll call it on each module and put it to SmartDashboard. Yeah, and you know, none of this is like the important values. All right, well, none of this is values that we really need unless it's debugging. Next up, toggle mode, brake, and coast. All of these are things that I implemented as part of a drivetrain thing. So basically, what we do now is that in robot.java, anytime we do teleop in it, we switch the drivetrain into brake mode, and anytime we go into disabled in it, or autonomous, important to do both of those. And then anytime we go disabled, we wait 1 second for the robot to actually stop moving, and then we switch the drivetrain into coast mode. This was more important when we had a tank drive, which meant that you could push the robot around nicely because otherwise it would be braking. And now the swerve modules are like all at weird angles so that you still can't really do it. But like if you want to spin the robot around, then you can move all the modules before you disable into that turning position. And then when you disable, you can just spin the robot and it'll spin freely because it's in coast mode. Same thing if you want to drive like forward, you know, push it forward, all the modules will align. And then when you disable, you can just push it freely in that direction. And it's nice and easy. And so that means, yeah, all the motors, turn motors, the drive motors, they're all just in coast mode. And so in order to achieve that, it passes all those calls down to the swerve module thing, which there's a toggle mode one, which is old, but it's much safer to use brake and coast directly so that they don't get out of sync and then we aren't coasting while driving, which is dangerous. And so if we're told to brake, then brake both the motors. If we're told to coast, coast both the motors. And then there's also a max turn velocity here, which is used up above. Right? That is everything in the main package. Great. Next, let us close all of these files. No, close all. All right. First things first, I'm going to quickly address this logging package. This was some code that I wrote back in like 2019, 2020, which is meant to like, it lets you log stuff, which is basically SmartDashboard values, and it lets you print messages to a message log. And WPILib has introduced something that basically does the same thing, but without all of our without logging it to our specific files on the robot and stuff. And so it's nicer. And go here, read all of the ignore that. And so you can read all this, and it talks about how their data logs actually work. It is much nicer than this API here. And so all of the classes have this deprecated tag saying use WPILib's thing instead. So I am not going to talk about any of that. If you want, you can read the code and see my implementation of all this stuff. But yeah. Now, stuff that we still use. Path. So path contains all of our robot pathing code. And the main class here is RobotPath. I will talk about these other ones after this because this is the main one. So for constructors, it takes in a path name, and in order to make PathWeaver work, the way that you do this is when you open PathWeaver, it'll ask for a directory to put the path project in. So set that to be PathWeaver inside the deploy directory to make it work. So right here, and then you can write your paths, and it will create all these path files, which are basically CSVs and stuff. Yeah. And then it takes in a drivetrain interface. Reasoning for that is that because we don't have an actual drivetrain class in Lib199, drivetrain interface is an interface which drivetrain can implement. So you can see that this is the swerve drive specific version, and there's also a differential drive specific version. That gives access to all the important methods from Lib199. Is inverted. That chooses whether the path is inverted, which let me make sure that I quote to you the correct definition for this. But basically, yeah, it's a reverse flag. Basically, I don't think you'll have to use this if you need to actually look up what it does. I've had to do it every time I've looked at the value, but it sets the reverse thing in the trajectory config. Let's see what this does. Does it do anything else? No, it does not. So yeah, it just sets whether the trajectory has this reverse flag on it. Which, let's see, that might mean that it tries to drive backwards or something. Regardless, don't use it. We implement our own way of actually inverting stuff. Yeah, translation 2D, this is basically an X and Y value. Where's the robot starting on the field? And this is, you'll see in a bit, we use this to initialize the odometry on the drivetrain. And so this says, if you say use this path to initialize the odometry, where's it going to say that is? And yeah, then that passes it to this get points from file function, which reads the path file from in here that we want, and then converts it to a CSV, and then these are all the values that are in that file. Basically, it takes all those and converts it into a bunch of poses which we can actually use. Then store all the important values. You'll see that drivetrain gives us the max speed and the max acceleration that it can handle. So then some other methods on here. There's a get rotation 2D, which gets the rotation of the nth pose of the trajectory. Okay. Did you say something, or did you just unmute?
I just unmuted.
Oh, okay. Then this is the main thing that you'll see us use with RobotPaths, which is getPath command. And this takes this path and it converts it into a command where if you run the command, it's going to try and follow that path. Keep in mind that this more or less assumes that you're at the start position of the path, because I wouldn't try it the other way. My guess is the robot's going to try to drive to the position on the field where it thinks the path's supposed to be. But yeah, you can see that we generate the trajectory if we haven't already, and this is because I'm pretty sure there are some functions on here which might try and edit the trajectory configuration settings before or between the constructor and the path command. Maybe, I don't remember, but that's why we generate the trajectory here. Then HS is our heading supplier. So it should be initialized up here, right? Oh, it must be set up as part of the trajectory stuff. Huh, where's this set? 1 second. HS equals. Yeah, so when we generate the trajectory, we create a heading supplier, which essentially is a double supplier of the trajectory, or of the rotations that we're trying to get to at the trajectory. So at each point, what rotation are we trying to be at? Or, sorry, it's not at each path point. That would be nice because we could do some cool trajectory interpolation with swerve really easily. But rather it is at every time index. What do we want? Where do we want to be facing at this point in time? And yeah. So then there is...
one question I have. So what is the inverted in the first method? I don't remember which one.
This thing?
It's inverted. Yeah.
Yeah, so that sets the reversed flag on the trajectory, and I was talking about how I actually don't really remember what that does. We could look it up by reading the documentation and such, but basically anytime that you use the class, just set that as false. And one of the reasons it exists is because we actually flag it over here when we reverse the trajectory, and I'll talk about that in a bit. So heading reference, what this is it is, why did we do it this way? So heading reference is, wait, run the robotics seeing the same direction? Yeah, but why did we do this in a supplier? Or why did we do this as a reference and not just as a rotation? Where's this used? .get degrees. It must be because we're trying to pass it into all of these suppliers and it has to be like a static thing or something. It's weird. Basically, the way you can think of this is it's actually just a rotation 2D. We just wrap it in atomic reference so that we can access it in ways that are useful to us. But for all intents and purposes, it's just a rotation 2D. And you call .get on it to get that value. So basically, get rotation of drivetrain is a fun method that we have down here because drivetrain interface itself doesn't expose a get rotation method. However, the implementations do expose get rotation methods. And so essentially what this does is we say, if we have a swerve drivetrain, then read its odometry and get the rotation of it. If we have a differential drivetrain, read the odometry and get the rotation of it. Otherwise, just use whatever is reported by the gyro because drivetrain interface does expose that. And the reason we can't just have like a unifying odometry thing to get is because there's a swerve drive odometry implementation, there's a differential drive odometry implementation, but WPILib doesn't provide an overarching odometry class. So we can't have that in the base drivetrain interface. So then this is desired heading, and this is going to say at each time which way do we want to be facing. So that's why we have taken these two variables, face and path direction and stop at end. If you are using a differential drive, then face and path direction will do nothing. So, but if you're using swerve drive and you say don't face in path direction, then rather than trying to, if you look at Pathweaver, you'll see that it draws like curves and such. So rather than pointing so that it's always pointing forward along those curves and driving forward, it will just face the same direction it was at the beginning and drive swervely following that path. All right? And so basically if we just want to stay facing straight, then when asked what direction do we want to be facing, return heading ref, so whatever direction that we've been facing or that we were facing at the beginning. Otherwise, return hs.sample, which is just, as I talked about, the direction that the trajectory says we should be facing. Yeah. And then for command, you'll see that we actually asked the drivetrain to create the command. However, and that's because depending on whether you're using a swerve drivetrain or a non-swerve drivetrain, they use different command classes. And so we just asked the drivetrain to do it. We give it the trajectory. We give it the heading that we want to face, and it does the rest of the work. Stop at end. So if we say yes, stop at end, then afterwards, then after the command is done, it's going to run an instant command which just says dt.stop. And so that's really used at like the end thing in our classes. In our commit. So like if we have a chain of paths, then we'll set that on the endpoints, but in the middle we might not do that so that we just keep driving. And then it requires drivetrain. And then if we are not facing in the path direction and we're instead just going to be facing straight, then command, what is this doing? Heading ref dot set. So yeah, this is why we have a heading reference. Now I realize. So if we're instead going to be facing in the path, or not facing in the path direction and just facing in the direction we're facing before, we just want to stay in the direction before we run the path. However, get path command might be called way before we run the path. So like if we're setting up all our commands at the beginning, this could be called when we're like initializing the auto command, and it might not actually run the path until the end of the auto command, where we could be facing in a completely different direction than we read here. So what this does is it just says, before we actually run the command, then update this heading ref value to point to the actual current direction of the drivetrain so that we just don't turn, and then run the command. And then put number, blah, blah, blah. So desired path heading. So just log that to SmartDashboard and then return the command. The other important method that you'll see called from other classes is initialize drivetrain position. And what this does is it just says assume the robot is at the start of the path. And so if you look at like our auto commands and stuff, you'll see that the first thing we do after, automatically setting up all this stuff is get the first path, initialize drivetrain position, because assume that we are at that location. And we do that before every path because it proved to cause a little less jerking and such, but mainly it just says assume the robot's at the start of the path. So if the trajectory is null, basically if we don't have a trajectory yet, call the generate trajectory function to make it, and then call drivetrain.setOdometry. And setOdometry doesn't actually take in an odometry, but it takes in a position and a rotation. So, or a rotation, which is actually just the whatever the get heading is converted to rotation 2D. So whatever the rotation of the drivetrain currently is, and the position and rotation, which is what a pose is. It's a position and a rotation, and the position and rotation that the drivetrain that we're asserting that it's at, which is just going to be the initial position of the trajectory. Next up, generating a trajectory, pretty straightforward. We're going to create a config if we haven't already, and this is where some of this stuff comes into play. We're going to create a trajectory config if we haven't already, and then we're just going to call trajectory generator.generate trajectory based on the poses in the configuration, and update the heading supplier to a heading supplier which follows this trajectory, and I'll talk about what the heading supplier does later. Next up, trajectory config. To get a trajectory config, really, what we could do is we could get rid of this, and instead of config, put get trajectory config, but whatever. If we don't have a trajectory config already, create it, and then return it. And to create a trajectory config, then initialize a new one with get max speed and get max acceleration. And then what we do is we then call drivetrain and we say, all right, now we've created our version of the trajectory configuration. Now do whatever you have to do in order to make sure that this configuration works for you. And so like you'll see in, I think, SwerveDrive, we have an implementation of this which adds a SwerveDrive kinematics constant, which says make sure that however we're driving the trajectory, it follows basic swerve rules. And then reverse it if we requested it. The other thing we have here is a robot path reversed, which basically says, which basically says we're at the end of a path, now drive the entire thing backwards. And so what this does is it flips all the poses around and it creates a new robot path with that reversed flag set. And that'll be a new robot path, which is the inverse of this robot path. I talked about get points from file already. This is just getting like max acceleration stuff. Set max acceleration. What does check config do? Config's already been created. Yeah. So this is why we have this is why we don't create trajectories and stuff immediately, is because on the path you can specifically set the max acceleration for this path or the max speed for this path. And so you can do that after the constructor, and the only requirement is that you do that before you call config or before you have to generate the trajectory. And so we just quickly check the config and we say, warning, you've already made a config. So we're going to update the variable locally because we can, but it's not going to actually have any changes because there's already we've already done the work of generating the config. These values have already been used. They won't be used again. Get path file, it just does that get deploy directory stuff. You can see it searches for pathweaver/paths/pathname.path. That's just deploy pathweaver paths pathname. Next up, here's the get rotation of drivetrain method. I talked about that. And here's the heading supplier. So basically what it does is whenever you start driving a path, it will, whenever you start driving a path, it will start a timer. And that timer will say, how long have I been driving this path for? And so what that then does is it says, after we've driven, just take this. Oh wait, no, I already pulled. Yeah, never mind. Is then after we've been driving for however long, so after we've been driving for however long, just if we're asked where should I be turned, then just return wherever the trajectory says we should be facing at this point in time. And then to reset it, when we reset it, we just reset the timer and say that it hasn't been started, blah, 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 blah. And where do we call reset again? So yeah, every time we get the path command, we call reset. One thing we should probably end up doing, instead of calling reset here, we should do command dot, we should add it as an instant command before the command is run. Probably. Yeah. Add that to our to-do list of things. All right. That's RobotPath. Now I'll talk about Drivetrain Interface. Basically, it just exposes all these methods. You should have seen where all these came up in the code, and they should be self-explanatory. However, there are two implementations of this that do things in a way which makes it easier to implement for their drivetrains. So like for a differential drive, you'll see that we expose a few more methods. So for a differential drive, if we have a method that we know will make it drive with a left speed and a right speed, and a method to get the kinematics, to get the max volts, to get characterization and all this, then we can have the drivetrain can adjust the creation of this ramset controller, which is the actual thing which will adjust, which like has configuration values for how you can think of it kind of like PID again, but this is for pathing, and so it has some configuration values for that. If the drivetrain wants, it can change them. By default, we just use the WPILib defaults, which work fine. And so to configure an auto path for a differential drive, it will get the trajectory config, it will set the kinematics object on it, it will set the kinematics to the kinematics provided by the drivetrain, it will automatically add a drivetrain characterization constraints which will work for this drivetrain. And when we create an auto command, we use a ramset command. We give it the trajectory. This function says what's the odometry position. New ramset, give it the kinematics object, pass it the drive function, and it requires this, which is drivetrain interface is a subsystem, because drivetrain's a subsystem, and so this doesn't matter. And so what it means is that then when we create the command, we can say require this And even though we're an interface, we're still a subsystem. So we can require the drivetrain interface, but when we run it, it'll require the drivetrain. So, and then to set the odometry, we just convert these into a differential drive odometry and pass that to a set odometry method, which will be implemented on the actual drivetrain. Now, Swerve Driver Interface is the one that we're currently using because we do all our stuff on Swerve because it's cool. So instead of driving based on left and right speed, we drive based on a SwerveModule state, on an array of SwerveModule states. We can get the kinematics, we can get the odometry, we can get the PID constants, we can set the odometry to a new Swerve Drive odometry. And then here are our implementations of these methods, and that's what the default thing does. So when we're configuring the config, we are just adding a Swerve Drive kinematic constraint based on the kinematics values that we have. And then when we are creating our autonomous command, we essentially have PID controllers that we create for the X, Y, and theta, which is the rotation. So, you know, we have PID controllers for the driving and turning on each motor. These are PID controllers for the whole robot. And then you saw the enable continuous input thing in SwerveModule. This is the same thing, but in radians, because radians. And then, yeah, then we're creating a SwerveController command. This is why it's different. And this does, same idea, pose mirrors kinematics, takes in all the PID controllers. Difference here is that we also take in this desired heading. And this means that the, and you'll see that in the differential drive interface, we ignore the desired heading. Because in Swerve Drive, we can point in whatever direction we want and still drive the path. In differential drive, we have to be pointing along the path in order to drive it. And so that's why we do that. And then once again, it passes in the drive method and this drivetrain, set odometry, we're just updating it with a new Swerve Drive odometry. Here's kinematics, here's the angle and the pose. Bada bing, bada boom. That is all of pathing. Next up, sim. This is our package for all of our simulation related stuff. And yeah, this will be the last stuff. So first we have the cancoder, so this is our mock implementation of cancoder. If you remember, I talked about how this one's different. This is because with cancoder, the cancoder more or less works with simulation. We just have to link its values to SmartDashboard. So when we create it, we just give it the cancoder, and then we're going to store the device ID, and we're going to create a sim device. And this gets into the whole WPILib simulation stuff, which I guess I should actually talk about. Basically, anytime that we have a WPILib device simulated, or something we want to simulate in a simulation, we create something called a sim device. And WPILib supports a whole slew of different devices. So like you can simulate encoders, and you can simulate all kinds of things that it'll do automatically. But for a general device that isn't one of the default WPILib things, you get a sim device. And it's kind of like SmartDashboard in that you can have doubles and you can have ints and all this. Actually, I think it's just doubles and booleans and some other stuff. And this will communicate it over to any simulators. So, yeah, we're going to store the device, and then on it, we're going to create a double, which is called count, that's going to be input, which means that it's going to be fed from the simulation to us. And what does 0 do again? And its initial value is 0. And now, cancoder doesn't directly connect to the simulation API, but it provides this class cancoder sim collection, which allows us to essentially simulate it. So we're going to cache that as well, and we're also going to add to the periodic methods. I mean, really, you could do simulation periodic, but if this is being run, we're in a simulation already, so, you know, who's to say what's simulation and what's not? So then we're going to update. So then every time periodically, we're going to update the position that it reports with the position that we're reading from the sim device, which is basically whatever the simulator is telling us our position is, that, and then multiplying by CPR. So basically, this is in rotations, and this converts it into actual cancoder units. Next, mocked Spark encoder. So this will simulate a encoder on a SparkMax. So when we create it, it's going to take in an ID, which is used on the simulation network. Again, just how we have CAN IDs, we have simulation IDs. They're the same thing, and we use the same numbers. So we're going to create a device. This is going to be its name, canencoder_SparkMax. This is going to be its ID. So you can think of this like, yeah, basically device type, device ID. The distance per pulse value is going to be something that we are going to be, is an output. So it's going to be a value that we're going to feed to the simulation. By default, it's going to be 1. And I don't remember the units here. That might be rotations, units per revolution, position conversion factor stuff, counts per revolution. Oh, yeah, 4096. So distance per pulse times so yes, this is the position conversion factor. Oh my gosh, I went ahead and wrote out the differential, what in the world? The what's the word I'm looking for? Dimensional analysis for this. So this is the amount of distance that we're using per count of the encoder. So by default, I think it's just set to 1-to-1. But if we change it, then we can feed that to the simulation. And this means that like this means that when the user sets like a position conversion factor on the encoder, we don't implement velocity conversion factor because everywhere in our code that we use it, velocity and position are they're the same thing, just divide by seconds or whatever. Although maybe something we can add at some point. We can consider it. Actually, Spark encoders, our mock thing doesn't even support a get velocity method. So I guess that's because at least in the past, we've only simulated differential drives which don't care about the velocity, they just care about the position. And yeah, I guess. So maybe we can add velocity at some point, but we haven't really used simulation in a while, so whatever. In any case, what was I saying? Position conversion factor stuff? Yeah, so basically that way if the user says this is the position conversion factor, if you imagine our simulator, there's not going to be any gearing, it just ties it directly to the wheel. So then we can use this in the code to then scale the output that's being fed back and forth by that position conversion factor. And essentially this will tell, by whatever the user sets the position conversion factor as, we can then tell the simulation, that's your gearing. And then we also create a count, which is same thing you saw before. Get position, distance per pulse times count, set position conversion factor, just set that and return no errors. Set position, just convert that into whatever the units of count are and then set that on count and get position conversion factor. There you go. And that is that. Next up, SparkMax PID controller. So essentially, I'm not going to go over the full thing because you can see it, but basically what it does is it just maps all the methods onto an actual PID controller. Although I'm not sure if it's just the reference. I think, yeah, so at the moment, this doesn't actually tie into a motor the same way that an actual Spark PID controller would be, but we haven't used that feature in simulation yet, so we haven't needed to. So for the moment, it just sets all those values on an underlying PID controller from WPILib and lets it do the work. Next up, a Mock Phoenix controller. The reasoning for this is that we can implement the code for driving a Victor and a Talon, and because they're both Phoenix things, they're both basically the same code. So we have one class that does that, and then we can control it for a Victor or Talon depending on what we want. Or we can assign it to each one. So takes support, takes the speed, and then this essentially implements following. So if you tell it to follow a motor, then retrieve that, then whenever, so basically if this motor is, if there's another motor following this motor, or for every motor that's following this motor, then set that speed to the speed we just set this motor to. And so that's how we implement following. Get the speed. This is how you do a follow method. Basically, why are we doing it this way? Leader, get device ID, add. Follow map, get leader, add. So basically, the way that we allow us multiple motors to follow one motor is that each motor maps to a list of other motors that are following this, or really PWM motor controllers, because they don't have to be simulated. Although, if we're using simulation, they should be. So if the map of motors that we're following doesn't already have an array list in it, then create it and add it. Otherwise, just add it directly to the list. Then there's set inverted stuff. Just getting device IDs, and then when we close it, and then when we call close on it, so when this object is no longer needed and we call close, which doesn't really ever happen, but if it happens, then clear all the follow stuff and close the PWM stuff. Or close the underlying WPILib motor PWM that we are using to simulate this. Because rather than doing all of the create sim device stuff that we talked about before in the other stuff, this one just uses a PWM motor controller provided by WPILib, which already sets all the PWM specific stuff back and forth and does that simulation. So there you go. Now MockTalonSRX. So whenever we create a SparkMax mock, create a sim device to represent the SparkMax and have an output which will be whatever it's being driven at, what percentage that is. Then create a mocked encoder and a mocked PID controller. Then you'll see a lot of these classes actually have this. These last three have a create mock whatever in it, because it just simplifies the writing of code. So we take in port and a motor type, pass that to the SparkMax, and then create a mock for anything we don't know. Just assume it's a dummy controller, because we don't use. So if we fail to implement something, then use the dummy answer we talked about earlier. Just don't do anything, return whatever the equivalent null value is. So when we set, we check is inverted, and you'll see that this is basically the same follower code, except we're only following CanSparkMax's. Although you'll see that rather than actually storing motors here, we're just storing the motor output numbers. So this double, which we can set to set the motor output on the simulation network, because that's all that matters. And then we set that on anything that's being followed. To follow something, then you can read all this, but basically, are we even using invert? So at the moment, follow something with an inversion doesn't actually work. Something we should maybe fix at some point. But basically make sure that whatever happens in all the follow methods, it eventually gets down to this one, which adds it to the follow map. So this way, all the follow methods with different things just have all the calls for any follow method get funneled to this one method, basically. Get the speed, get device ID, get encoder, and then there's all these other things which we can actually probably ignore because they're covered by this DummySparkMaxAnswer. But if we ever wanted to change them, these are the methods that we actually sometimes use, and they just all return KOK. Get PID controller does that, and then to set a voltage, just call set with the percentage. And there you go. And then finally, MockTalon and MockVictor are pretty simple. They just create a motor PWM, which is Oh, yeah. So they just both extend this MockPhoenixController class, and they set up this motor PWM, which is the underlying PWM controller, which we're using the WPILib simulation of. So we're doing that with either a WPILib Talon or a WPILib and then to create a mock of it, we just create mock type, class, new ErrorCodeAnswer. So if for any methods we don't know, use that Phoenix ErrorCode response, and then it's going to implement auto-closable. And that, I believe, I have no idea what I opened. And that should be every single file in here with the exception of logging. And I also didn't go over this ConvertPaths.py because it was written once in our 2019-2020 year to do some pathing stuff, and we haven't really used it since. I don't even remember what it does. Yeah. All right. That is everything. Any questions?
I'm assuming you're not going to show swerve, but you want to show the simulation thing. Just like
So it works. I've been simulations to this. So it's been a while, and I don't fully remember how it works. I will try. See here. Take this. I previous project. Right here. All right. I think that's it. Let me see if it works. It may not. So I have a controller here. This button. You want to fire here. It goes on the post. Here we go. Let's see if it works. Okay. All right. This is the simulator. And now we're going to go to the world that is in this project. And by the Drivetrain. Let's just run it and see if it works. Here we go. Why is it like that? Where's the other one? Okay, let's try. Yeah, I want to see if I can this. Where's here? Yeah. Take extension. I don't know why it does this. We just found it last year as well. And I don't remember how to fix it. I'm just finding the data. There we go. Changes. Yeah, I know. There's something needs to work. I mean, here, you can kind of oops, man. Let me undo all these things. Oh. Yeah, no, move it. Sorry, guys. And yeah. So it's like that, we're going to get that, get rid of. Okay. Set up a joystick. Here is the window. And let me just make sure that that works, and then view. How do I? Hey, it works. You still there?
Yeah.
Yeah. There, I got it working.
Nice. Well, like, we never really use it, though, so...
This is the extent of our simulation abilities, and you can't see it because this is just sharing my screen, but I actually have my PlayStation controller hooked up to the computer right now, and that's what's doing this.
But yeah, I don't... Are the, like, the mock classes only used to make... well, nowadays, they're only really used to make sure Rev doesn't mess anything.
Yeah, basically.
Oh.
But we spent many fun days. Essentially, you can play around with this simulator and a bunch of weird stuff happens. Here, let me mess with this field a bit. There. Now that we have, whoa, I forgot how to control this thing. Let me, where's our robot gone? There it is. Wait, I can do this. Go to viewpoint, follow robot, invalid solid name. It's totally not an invalid solid name. Ah. Let me make this work somehow. Children. Oh yeah, I have to do a solid. What? It's totally right. There's a way to make this work. I don't remember it. I figured out how to do it previously. We can just zoom out a bit. So basically, the simulator tends to glitch out, especially when you do things like this. So the robot's now upside down. And then you can... It's fun. Yeah. I don't know. Yeah, that's all I got, though, I think. Here. Bigger robot. And it's gone. Yay. Oh, cancel. Yeah, so that's what we got. Anything else? All right.
That's just for the video part, right?
Yeah, I'm actually still recording this, but I think that what I might do is, you know how I was talking the other day about a joystick like util class?
Yeah.
I might go ahead and program that and then make an addition to this where I talk about how to actually update Lib199 yeah, using the new system.
Yeah, you should do that.
Yeah.
But once you stop recording, I was actually gonna talk about something.
Oh yeah, here, I will stop recording. All right, audio is recording. See ya.